Hi, I'm Jack Buffington for RobotBrigade.com. This is the first video in a series of videos about the software that I am running on my microcontroller for my mapping robot. In this video, I'm going to talk about the main program and how it works. I'm using the Propeller microcontroller, and it has two languages that are native according to Parallax, though there are others out there. There is Spin, which is an interpreted language that can be interpreted directly on the propeller. And then there is PASM, which is Propeller Assembly. This particular program is written in Spin, which is somewhat like Python or Pascal. It has a little bit in common with something like Verilog. Anyway, let's just get started looking at the code. Up here I have a constant block, and this is a block of code where you define constants. And so I'm defining that I'm using an external crystal with a 16 times phase lock loop. I have a 5 megahertz crystal. These are some constants I'm using for my battery. These are constants that are used for telling it what pin is associated with what signal, so I don't have magic numbers all throughout my code, though I still have a few of them. This is a object block right here, and it is basically if you are it's saying what files are used with this program. If you're a C++ programmer, these are like pound includes, or if you are a young C++ programmer, it is a hashtag include. PWM, I should say all these up here are programs that hog a core. The Propeller is an 8-core microcontroller, and so each one of these is using a core. So I have a core doing pulse width modulation. It's doing 4 channels to drive the H-bridge for 2 motors. I have a serial core. It can do up to 4 serial ports, but I'm using 2 at the moment. I am doing 2 encoders, though this code can work with up to 16 if you don't want to have a way to output anything. I have my velocity controller that is allowing you to set the velocity of the motors. And this controller, you tell it what velocity you want it to go, but it will actually ramp with an acceleration. So the velocity can be, say, at stop, and instead of going bang right up to another velocity, it'll ramp right up real nicely. I have an analog to digital converter core, and the Propeller does not have an ADC. However, it has timers, and these timers can be set up in such a way that they work to mostly implement sigma delta analog to digital conversion. And this is the first time I've used this on the Propeller, and it has worked great. So I'll definitely be doing that again. I have an I2C core, and finally I have a bit of code that I wrote that is purely in Spin, so it doesn't hog a core that drives the OLED display. Of these, I wrote the pulse width modulation, the encoder, the velocity controller, and the OLED. The rest came from Parallax's GitHub account, where they have all kinds of code that they have written themselves or has been contributed by the general community of programmers that use the Propeller. Here I have a variable block. The Propeller, because it is a multi-core system, has hub RAM, which is common RAM used by all cores, and each core has 512 longs of RAM that is exclusive to itself. And when you launch a program into a core on the Propeller, you typically pass an address of a variable in hub RAM. And so my PWM and encoder and velocity controller are all using these variables here. And because I can only pass one address, it's very important that you keep all these in this order with no extra variables tucked in. Based on that first address that you give it, these programs can calculate the addresses of the other things as long as we stick to this predefined order. These variables here are in no particular order and are used in this program. Now I have a pub block, and this is basically a function or subroutine in Spin. The first thing I need to do is turn the power on, or keep the power on. The power controller IC that I'm using looks for an input, a high signal on one of its pins just after starting up, and if it doesn't see it within a certain amount of time, it shuts the system power right back down. So if your processor has failed, it will shut back off. So it's important to get this back on, and I think I have about 65 milliseconds to do this. The next thing I need to do is set the directions of the pins. So in the propeller, the direction is whether it's an input or an output. And then when I set the output state, that's saying is it a high or a low. And these two lines here are turning on the power to the CPU and to the motor controller. Next, I am starting up my serial ports. I start up I2C and my OLED where I display a message on it. Start up analog to digital conversion and play a couple beeps on the speaker. Starting up PWM, starting up the encoders, starting up the velocity controller. The velocity controller is actually at its heart a positional controller. It's just that I am adjusting the position rapidly to achieve the velocity with acceleration. So it's a PID positional controller at its heart. And PID stands for proportional integral differential control, and it's a common strategy used for driving motors, if not the most common. These are some variables here that are used in this program, and here is the meat of the program. It's the loop that constantly keeps the whole show running. So I'm monitoring the button. What this is doing is it's counting button presses and determining how many presses there have been, and if it hasn't been pressed within 1 second, it sends that off then to the Raspberry Pi. Here I have a state machine where I'm looking for a serial message. When I have received a complete message and it checks out, then it parses it and does what the Raspberry Pi has asked it to do. Here I'm monitoring the battery voltage. I'm looking for the CPU to, if it has shut down. So that's it for the main loop. Here's the function for starting the serial ports. I'm just launching 2 of them. One of them is on the programming port so that my host PC can get messages, which is sometimes useful. The other is for the Raspberry Pi. Both of them are at 115,200 baud. I have 2 different beep routines at the moment. Happy beeps, doo-doo, and sad beeps, doo-doo. And then my beep routine, this figures out how many cycles it needs to toggle and then does the toggling. I am doing a wait here where the propeller has a system counter that is constantly incrementing, and this is a 32-bit counter. And wait count says wait until the counter equals, in this particular statement, the counter plus a half of a period for the particular tone that I'm trying to produce. And this works just great for doing this. Previously, I had made a mistake where I figured out, okay, well, here's my duration in milliseconds. I'm just going to add that to my system counter. And then here I have a repeat loop that's looking for when the system counter is greater than that value, then it will just stop. But the reality is because this counter can loop around or roll over, sometimes my beeps would get truncated, which is no good. So that's why I have it written the way it is. Monitoring the button. This is a non-blocking routine that's looking for how many times the button has been pushed. I'm not doing any debouncing because it seems like the other routines in that main loop take enough time that I haven't needed it. It's always given me an accurate count of how many pushes there have been. Once the time has elapsed, it creates a message to send to the CPU and sends it. Monitoring the voltage. If the voltage is too low, it just shuts off. If it's just kind of low, it sends a message to the CPU to say, hey, the battery is low. And then it makes sure it only sends it once. This is the functions it's calling, which is actually defined right here. And it just is creating the message and sending it off. Reading the battery I used down below. Technically, I could have called it up here as well, but I didn't. I've just duplicated code, which is generally bad form. But it's just a one-liner duplication, so I'm going to let it go. So looking for CPU shutdown, I'm monitoring a pin on the Raspberry Pi. If that goes low, then my current behavior is to just shut off the motors and the microcontroller as well as the CPU itself. I'm not providing power to it either. Looking for a serial message. This is a non-blocking state machine that it hangs out looking for a start byte. When it has seen it, it moves on to the second state, which is looking for the next byte that it receives, which will indicate how many bytes are in the message. Then it will go ahead and receive all of those bytes. While it's receiving them, it is also calculating a checksum by performing an exclusive OR of those bytes. The Raspberry Pi has also computed the checksum for the message and stuck that at the very end of the message. And so when this gets to the very last byte that it's supposed to receive, if the resulting checksum is 0, then the message was good. Because prior to that last byte, the checksum should equal what the microcontroller has also calculated. And then when you do the exclusive OR of a value with itself, it will equal 0. So here, if the checksum equaled 0, then it goes ahead and parses the message. And so I have a few things that I can do. I can display a message to the screen, the OLED display. I can do my beeps. Right now I'm only doing the happy and sad beeps. I can drive the motors. Of course, when you're receiving data through a serial port, you're getting it as bytes. So I'm receiving 4 bytes, and then I am converting them into a signed long, which is sent to the velocity controller. The CPU is shutting down. I am not currently using this. However, this would be useful for if you have driven to a docking station to charge the battery. Maybe you received the low battery warning, you drove over to the docking station, and the CPU could say, I'm shutting down, and that could cause this propeller, though it doesn't currently do it, it could put it into a state where it says, okay, let's just hang out for 2 hours and then start everything back up. Or let's hang out until the battery has hit a certain voltage and then start everything back up. Here the Raspberry Pi can request the voltage, it reads it, and then it creates a message and sends it off to the Raspberry Pi. And then finally, this alerts the microcontroller that the CPU has finished starting up. Right now it doesn't really do anything other than display to the screen that it has started up. So this is the main program. I'm going to go and talk about, in future videos, I'm going to talk about the other code that I wrote. And if you found this useful, you might check those out. For robotbrigade.com, I'm Jack Buffington.